Good morning, everybody. I'm Tommaso Turrin, and now I will introduce you to our project called Coupling with Adjustable Torsional Stiffness. To well understand the meaning of our project, I should start to make clear the meaning of these two words, coupling and torsional stiffness. Coupling are mechanical components used to connect two shafts in order to transmit power. You can see some examples here in the picture. Here you can see two examples, for example, of two different systems where we can find uncoupling. And here is an example of a typical coupling that we can find in those systems. While torsional stiffness can be understood watching the second image and following the graph. As more torque is applied to the shaft, as more angular displacement we will have on it. The slope of the graph is its torsional stiffness. The torsional stiffness can be also represented here as a formula. The image is explained in the same concept that I've already explained. But how are these two concepts related to each other? Well, these systems have to run in wide frequency ranges, and resonance must be taken into account. Resonance occurs when the frequency of an applied periodical force is equal or close to the natural frequency of the system. Here we have a video where you can directly see the consequences of having a system in resonance, so the torsional vibration of the system are getting higher and higher until reaching the breaking point of the helicopter in this case. So why do we need a coupling with adjustable stiffness? Here we can see the simple natural frequency formula depending on mass and stiffness of the systems. Since we can't change the mass of it, the goal was to find a way to change its stiffness, obtaining variation of natural frequencies of the system. Knowing the definition of resonance, we know that changing the natural frequency of the system, we can so avoid the phenomenon of resonance.
Okay, next is the coupling design. The goal of the project was to design, manufacture and test a coupling which would have an adjustable torsional stiffness. We designed two different couplings. First one on the top right is beam coupling, where beams are used to adjust the torsional stiffness, and lower right is the spring coupling, which uses springs to adjust the stiffness. In the end, beam coupling was chosen to be manufactured and tested. Okay, let's go over some parts of the coupling. First we have the input half, where the motor is attached. Then you have beams and the adjustable flange. Then we have middle shaft and the output half. On the left you can see a section view of the coupling. The coupling works when we attach a motor on the input half. The torque gets transferred to the beams to the adjustable flange. From the flange it goes through middle shaft, which is fixed on the output end, and the output half transfers the torque to the rotor. The stiffness of the coupling is adjusted by changing the effective length of these beams. On the bottom right you can see a typical cantilever beam. The effective length is the distance between the clamp and the force. When we increase this distance, the beam starts to bend more. We are basically using the same principle in our coupling. The effective length is the distance between the input half and the adjustable flange. Basically, we are moving the adjustable flange to change the stiffness. The middle shaft is fixed on this end, so when we are moving the flange to the right side, the effective length increases, so the stiffness decreases. And when we're moving this adjustable flange to the left side, the effective length decreases and the stiffness increases. The manufacturing was done in Aalto University lab. On the left you can see the milling of the input half. On the middle you can see threads being made to the output half, and to the right side you can see the cover of the coupling being made. Here we have a couple of pictures of the manufactured coupling. On the left you can see the coupling assembled and ready. On the right you can see the coupling installed into the Aalto University rotor lab test bench.
We tested the stiffness by attaching the coupling to a lathe. This side of the coupling is fixed, so it cannot rotate. This side can rotate, and we measure the displacement here. From this displacement value, we can get the rotation angle of this side of the coupling. We exert torque here with this wrench, and there's a weight hanging out of it. From this display, we can read the torque values. We obtained stiffness versus central disk position curve. On the y-axis we have the stiffness, on the x-axis we have the central disk position. Here with black stars we have the experimental data. As we can see, we get a good range of stiffness. We get higher and lower values compared to the previous coupling that was used in this application. Analytical and simulation had a much higher stiffness values because they didn't take account these plastic parts here which have a low stiffness. In the future, we could measure how the stiffness affects on the natural frequencies of this kind of system where the coupling is attached to a motor and a rotor.